Hello, everybody. Welcome to our first day of section 3.3. Now, in your notebooks, if you did want to just make a note, 3.3 will actually all be about graphing. Square roots, and cube root functions. And we will have board notes as part of tonight, but we're actually going to start with this Venn diagram. But if you want to get your board notes ready in your notebooks, you can add this title on a new page, 3.3 graphing square root and cube root functions. And to start off this conversation, we're really going to focus on the characteristics of each type of function. So the entire left side of the Venn diagram is going to be dedicated to the square root function. And as of now, I'm going to try to switch over permanently to a skinnier pen because the chunkier one, it's not going to work out for me in terms of space. I actually tried recording this already, and I ran out of space because of the chunky marker. So here goes a second try with a skinny one. Square root function. Nah, that's not skinny. That's better. Okay, square root function. The general form of a square root function is y equals a times the square root of x minus h plus k. On the right side, we're going to have the cube root function. Which is going to be the exact same function, but instead of a square root, we have a cube root. Let's start talking about the square root function. The graph of a square root function either looks like a starting point here and then a curve that's increasing, or a curve and that decreases. Square root functions are the inverse of a quadratic function. And if we think of the shape of a quadratic functions are like so, these U parabolic shapes. Now, the reason why these look like a piece of a U is because we only graph top or bottom to keep it a function. What we mean by that is if we were to literally turn this U shape sideways, that's what the inverse technically looks like. But that would definitely fail the vertical line test. So instead, notice you're either graphing the top or the bottom. That's where that split quality comes from, either the top or the bottom, because otherwise it would not be a function. Let's come over here and talk about cube root functions. Cube root functions are the inverse of a cubic function. Cubic functions, if we remember from our parent function chart, look like so. So if we turn this one sideways, the graph of a cubic function is either increasing left to right with that bend still in the middle, or starts high and then comes low. So literally visualize this vertical shape being turned sideways. No special comments about only top or bottom because this will always pass the vertical line test. There's no worries about restrictions on that. A similar note, there's a nice connection to the fact that we cannot have negatives under a square root. We can't have negatives under an even root. So not all values of the domain are allowed. We'd have to restrict the domain. But for an odd root, we could have negatives underneath an odd root. Hence, no restrictions at all on the domain. Okay, coming back over here to square root functions, let's talk about a. Oops. We have this drawn over there, so I'm not going to keep it here. But if you can, I just don't want to take a chance of running out of room. Okay. If a is greater than 0, it means that it has a starting point and it goes up. It's increasing. If a is less than 0, starts high, decreases. So you could kind of think of it as if a is greater than 0, you've got the top half. If a is less than 0, you have the bottom half. That same increasing, right, this is increasing left to right, decreasing. If we come over here, same applies for our cube root functions. If a is greater than 0, starts low and increases left to right. If a is less than 0, starts high and decreases left to right. HK, which we've seen with absolute value functions, quadratic functions, and now we see them here, HK, with our square root and cube root functions, is, as always, a very important point. For square root functions, h comma k is the starting point of the graph. So it's that value right there. It's that ordered pair where it starts. I'm going to switch over to red just to make this clear, and bear with me as I change the line thicknesses. That's what I mean by starting point, that value right there, that ordered pair. Coming over to the other side, for hk for a cube root function, h comma k is called the point of inflection for cube root functions. Another name for it is the center point, also known as where the graph changes, where the change in concavity takes place. Now, blast from the past, don't write this down. With quadratics, this was concave down, and this was concave up. We kind of see that same curve right here. See how this is like concave up and then switches to concave down? This is concave down, switches to concave up. So that ordered pair, wherever that concavity, that curve kind of switches direction, like maybe it's here and here, where it switches from concave down to concave up to concave down. That's that value. So for each root function, hk is very important, but compare how differently it applies to each. For square root functions, h comma k is the starting point of the graph. For cube root functions, it's the point of inflection. It's that center point where the concavity changes in the middle of that graph. We already talked a little bit about how square root functions will have restrictions on the domain, and those domain restrictions are directly connected to h comma k. So let's write that down. Domain and range restricted by h and k. Domain will be h comma infinity as long as the coefficient of x equals 1. And as crazy as that sounds, you already know what this means. You may just not remember right this second. But if I wrote y equals a, and then this has to be 1. 1x. 1 has to be in front of x. Minus h plus k. Like, let me put off to the side here. If I had given you way back when y equals 3 times the square root of x minus 3 plus k, and I asked you for the domain, you would have focused on what was underneath the even root, which is x minus 3. You would have set x minus 3 greater than or equal to 0, and then we reasoned, hey, look, I can just pull out 3. X is greater than or equal to 3, so my domain was 3 to infinity. So 3 is h here. So what we're saying is that if the coefficient of x is 1, you can literally just identify what h is, say h comma k, and you have your domain. But if I had given you something like y equals, I don't know, negative 2 times the square root of 2x minus 3 plus 1, I'm just making that up. Your focus is still on underneath the radical, right? 2x minus 3. But I can't just say 3 comma infinity, because when I go to solve 2x minus 3 greater than or equal to 0, I add 3 to both sides, divide by 2, I end up getting x is greater than or equal to 3 halves. So that's what we mean by you can say that the domain is h comma infinity as long as the coefficient of x is 1. When you have this situation. As soon as the coefficient is not 1, you have a little bit of solving to do. The range will be k comma infinity and if we visualize that here, this would be a shift up 1, and then it would keep going on forever and ever. The question is, which way does it keep going on forever and ever? Well, if I have a positive a, I know that my starting point will be here, and it's going to go up forever and ever. So this applies to when I have a positive a, because my k value, let's say that we were graphing this one and it was shifted up 1, so this would be a y value of 1 to infinity, 1, comma, infinity. But if I have a negative a value, visualize what that means. I have a starting point and it's decreasing. I'm taking the bottom half. I come up from the bottom, that would be negative infinity, comma, k. I know I'm a little fuzzy here with that parenthesis. Almost look like it could be a bracket. Be crystal clear with your brackets versus parentheses. Still not so good. Good enough. Okay, so we've talked domain and range. Clearly we have restrictions because we're dealing with that even root quality. Let's talk domain and range over here for our cube root function. Cube root function. Just by looking at the graph, I think we can see something awesome. Domain and range have no restrictions. If we look at this graph, I come in from the bottom, I come in from the top, I hit arrows. Negative infinity to infinity for the range. Come in from the left, negative infinity, come in from the right, positive infinity. No restrictions at all. So we've talked about their differences. Now let's talk about what's similar. Let's talk about the middle. If we look at the location of h, in both, h is underneath the radical, x minus h, x minus h. Call to mind vertex form for a second. I'm just going to write it right here. You don't have to write it. Vertex form was f of x equals a times x minus h squared plus k. Or if you want to, I'm just going to put last from the past, right? This is the last unit. Because there's a lot of connections between h and k with quadratics and here. So think back to quadratics. What did h do to the graph? Well, with quadratics, h was a horizontal shift, and that will be the same here as well. H is a horizontal shift. Left or right. Just like with quadratics, we pulled out h. If I saw a positive h, I knew that a negative was plugged in. That would be a shift left. If I just saw x minus 5, we would say that was a horizontal shift to the right 5. Same concept here with h. What was k? With quadratics, that positive k value, or it could be negative, was a vertical shift, and that is the same here as well. K is a vertical shift. Up or down. When we talked about the effects of A with a quadratic, if we had a positive A, the whole graph opened up. If it was a negative A, the whole graph opened down. Now we're definitely having not so much an opening up or down, but an increasing or decreasing quality. So positive A, the graphs increase left to right. If it's a negative A value, they decrease left to right. So for example, here, when I look at my square root function, when A is greater than 0 or positive A, that is increasing left to right, less than 0, decreasing left to right. Come over here. This is a positive A value, left to right, increasing, less than 0, decreasing. When we talked quadratics, we also talked about the actual value, specifically the absolute value. When the absolute value of a was greater than 1, we said that that was a vertical stretch or pull. That is the same quality here. So if let me come over here. Let me point to the right function. Here, if I had 5 times the square root or -3 times the square root, take the absolute value, 5, 3, those are larger than 1, there would be a vertical stretch or pull, whichever way you like to look at it or hear it. They both mean the same thing. On the flip side of things, if the absolute value of a is between 0 and 1, what would you say when we dealt with quadratics? Like if a was 1/2, what would you say about the shape of that u? You would have told me that that was more wide. So same happens here. If the absolute value of a is between 0 and 1, that is a horizontal stretch or pull. So as different as these graphs look, notice how much they have in common in terms of h, k, and the effect of a. This will be a very, very useful Venn diagram for us throughout this section. Really reference it, and I hope it helps you kind of put the big picture framework in your head for the qualities and the characteristics. Let's get into some board notes. We're going to introduce the idea of graphing. So again, the title for these notes will be 3.3, Graphing Square Root and Cube Root functions. To graph. Step 1, identify h, k. And create an input, output table. 2, input numbers for x that will result in, and this is important, perfect squares or cubes. Depends on which function you're working with, once simplified. These are our 2 steps. The best way to practice is to actually do one. So let's do one. Example. Graph y equals -3 times the square root of x minus 2 plus 1, and determine the domain, range, and intercepts. And determine the domain. Range and intercepts. So let's follow our steps. The first step says identify h comma k. It's nice that there's similarity. With quadratics, x minus h was in parentheses. Now x minus h is underneath the radical. And then plus 1 is my k value. So h comma k is 2 comma 1. Because this is an even root, a square root function, this is the starting point. We're going to use that starting point to set up our input-output table. So we're going to say xy, and we're going to put 2 comma 1 right at the beginning of our table. This is our starting point. And I actually want to move this over because I want to make a note. I'm going to make some notes on the left. Now step 2 is where all of the strategy happens. It says input numbers for x that will result in perfect squares or cubes once simplified. So what we're saying is, imagine if you plug in 2 right now. Check this out. 2 minus 2 underneath the radical, that's 0. I can take the square root of 0. The square root of 0 is 0. The next possible perfect square would be the square root of 4. I'm going to make a note, goal. So what value of x would get the square root of 4 underneath there? Mental math, I'm going to choose 6. Because 6 minus 2 would get me 4. That's what I mean by the square root of 4 being the goal. The next perfect square possibility would be, what's the next perfect square? The next perfect square is 9. I'm going to make that a little bigger if it's hard to see. So here the goal was the square root of 4. X equals 6 makes that happen. The next goal would be 9 because that's the next perfect square. What would get me 9 underneath the radical? 11. Because 11 minus 2 is 9. That's what we're saying by input, strategically pick inputs for x that will result in perfect squares. Let's get one more. After the square root of 9, 2 squared is 4, 3 squared is 9, 4 squared is 16. That's the next possible perfect square. What would get me 16 underneath here? Well, if x was 18, that would happen. I don't know how these got so spaced out. Let me see if I can move them up a little bit. So what's in green is all in your head. I mean, if you want to make a little note, that's fine, but like put a little squiggle or something, or put this in a brain bubble. Because the actual table is what's here written in black. But where 6, 11, and 18 came from is because in my head, I asked myself, well, I want to be able to take the square root of a perfect square. If x is 6, 6 minus 2, I get the square root of 4, I can do that, and so on. The process repeats. So personally, if having this running list on the side helps, do that. It's having this in your head that gets me these numbers. Now we can actually do this. So mental math, 6 minus 2 is 4. Square root of 4 is 2. Times negative 3 is negative 6. Plus 1 is negative 5. If you would like to see that out, I will do it out. So y equals negative 3 times the square root of 6 minus 2 plus 1. that became -3 times the square root of 4 plus 1. That's the -3 times 2 plus 1. -6 plus 1 gets me -5. And we're just going to repeat the same process with 11 and 18. So either use your mental math skills or take a second and actually do it out. I'm going to pause the video, and when you press play again, the math will just be here for 11 and 18, and then what the values are for the table, and we'll see if we match. Press pause. Here's what I got. When I substituted in 11, mental math or do the workout, either way you get -8. Substituting in 18, we get -11. So let's draw a quick sketch here. Your ruler makes a great straight edge for setting up some axes. Visually, I see that I have X values this way and Y values more this way. So I know I'm going to be in this quadrant. So if I do small enough tick marks, I should be able to count by 1. I need to get to 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Ooh, super close. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, oops, 11, 12, 13, 14, 15, 16, 17. Okay, I made it to 18. That's 18. And then down, I have to get up to 1. That's not hard. Let's get to 2, 3, 4, 5. That's -5. 6, 7, 8, 9, 10. -10. 11, 12, 13, 14, 15. Now we're just going to plot our points. So 2, 1, 6, down to -5, 11, down to 8, and I might just kind of put a tentative dot, 6, 7, oh, see, 8 is supposed to be a little lower, more like right there. And then last but not least, 18, which I know is right here. Think right there, but let me check. Here's -11. Still a little high, more like right there. So pencil is key when you're graphing. And I know that H, K, 2, 1 was my starting point. So I know that that's my starting point. You'll have a better time with the curve. For me, sometimes on the Mobi, it's a little rough. But there we go. Okay, we've drawn the sketch of our graph. We were also asked for domain, range, and intercepts. So domain and range, let's do that first. Remember, H, K affects this. So this was 2, 1, H, K. So my domain, put it over here. My domain, when I come in from the left, 2 to infinity, because when I come in from the right, I hit an arrow. My range, I come in from the bottom, -infinity, K. So there's domain and range. Again, domain is affected by H, range is affected by K. Intercepts, I clearly see that because this is the starting point, I'm not going to have any y-intercepts. So no y-intercept, or no real y-intercept. The x-intercept, I don't know about that. I mean, it's definitely not 2, maybe it's 3, but maybe my sketch is a little off, and it should be a little closer to 2. So when in doubt, let's do math. So really think about what it means for something to be an x-intercept. It means that you want to go left or right, but you do not want to go up or down. So to find the x-intercept, let y equal 0. So let's calculate. 0 equals -3 times the square root of x minus 2, x minus 2 underneath the radical plus 1. And from our last section, we are expert solvers. So let's subtract 1 from both sides. Get -1 equals -3 times the square root of x minus 2. Divide both sides by -3. We're definitely going to work with decimals. I chose to hold off on decimals as long as I could, just so I didn't make any rounding mistakes, but maybe you turn this into 0.3333 and see how it goes. Me, I kept it 1/3 for now. We will square both sides. That gets us 1/9 equals x minus 2. I would not write check here because I clearly see that that point does exist. I will add 2 to both sides. To write 2 in terms of ninths, I want to see that as 18 divided by 9. So I get x equals 19 ninths. And when I divide, I got x equals 2.11. If I look, that's definitely a possibility. I mean, if I had just curved it a little bit more that way, I definitely would have been more to the side of 2. So our x-intercept at 2.11, 0. Very nice. Let's wrap up today by actually taking out our graphing calculators. So go ahead and pause if you don't have your calculator out yet. We're going to graph this and see how that goes. Okay, so I'm not actually sure where I just paused it. If I'm about to say the same thing again, I'm sorry. So I just mentioned how I see that it says error here, and if I look at either my sketch right here, or more specifically, if you go back to your calculator and you hit graph again, there are no, for any x value less than 2, there is no graph. So it makes sense that when you hit second table, it makes sense that you see these errors. Here's our starting point, 2, 1. And the first thing I noticed that made me laugh when I just looked at this here, 3, -2. I'm like, but wait a second, I didn't have that in my table. So when I came back over here, I was like, oh man, I totally forgot about the square root of 1. I was so quick to jump to 4. But 1 is technically the next perfect square, or first perfect square, depending on how you look at it, after the starting point. So to get a 1 underneath the radical, if x is 3, 3 minus 2 is 1. So technically, I could have had 3 here as a value, and that would have been 3, whatever it said. I think it was -1. Let's go look. No, -2. So if we had plugged in 3, we would have gotten a -2. So let's see what else we see. After that one, which I missed because I was so quick to think about the square root of 4 instead of the square root of 1, notice decimal, decimal, 6, -5. I have to switch views, but you can look at your notes. 6, -5. So between 6 and 11, let's see if we see any whole numbers. No, 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 no. Scroll down. Nope. Whole number, 11, -8. Let's see what the next one is. Decimal, 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 decimal. Whole number, 18, -11. That was the next one in our table. So that's the power of this strategy of specifically choosing inputs, values for x that will get you that perfect square underneath the radical. And don't be like me and forget about the square root of 1. You'll be just fine. Either way, we're fine. We had these 3 points. That was enough. But it just literally made me laugh. And it could be that it's a little late and I'm a little tired. But as soon as I saw Let me come back up here. As soon as I saw that 3, -2, I was like, wait, what did I miss? And then I saw it. So using, oops, didn't mean to go up that far. Now you know how to input the square root functions into your calculator and use your table to back up your work. I do expect you to know how to make these good choices and create your own table. But the graphing calculator can be a great backup to know, did I pick the right values? Like for me, I would have seen, wait, I missed square root of 1. Did I pick the right values, and did I get the correct outputs for those values? Nice job, everybody. I hope you have a great night. Any questions? We'll talk about them first thing tomorrow. Our notes are all set for today. Have a great day. Bye. Oh, well, let me adjust that. Tomorrow in class, by that I mean tomorrow, since this is a flipped night, you'll be working on the 3.3, day 1 and 2. We'll start working on that homework assignment. And with that, I now officially say, have a great night.